Welcome back. I've got here on my bench a MAX31855 thermocouple to digital converter, to be exact, a thermocouple to digital converter to K-type thermocouples. So it's the 31855K. And I've got it a while ago in some mailbag. A card, a link in the description. I also got my trusty Arduino Nano here. And yeah, you guessed it. We will connect both of them to read some temperatures from that thermocouple. I should also mention that a while ago I made a series of videos about the MAX6675 K-type thermocouple to digital converter. The basics, card and link in the description, and there will be some comparison going on. So let's have a look in the datasheets of both and see what the actual differences are. Both are cold junction compensated thermocouple to digital converters. However, the 6675 is only available as key type thermocouple to digital converter, while you get the MAX31855 as key JN, TSR or E-type thermocouple to digital converter. Both sport a 0.25 degrees Celsius resolution, but the MAX31855 has a higher temperature range from minus 270 degrees Celsius to 1800 degrees Celsius, while the 6675 only goes from 0 degrees Celsius to 2024 degrees Celsius. Consequently, the MAX31855 has a 14-bit resolution and the 6675 only a 12-bit resolution. As far as accuracy goes, they're basically the same. So the 31855 sports plus minus 2 degrees Celsius in a temperature range from minus 200 to plus 700 degrees C, while the 6675 has 8 LSB, an LSB being 0.25 degrees Celsius, so 2 degrees Celsius, so plus minus 2 degrees Celsius, in a temperature range, of course, starting at 0 degrees Celsius to 700 degrees Celsius. Both feature a detection of an open thermocouple, but in addition, the MAX31855 also sports a detection of thermocouple shorts to ground or VCC. That will become important in just a second. Both have an almost identical typical application circuit. The converter and SPI interface to the microcontroller, 0.1 microfarad decoupling capacitor between ground and VCC. However, the thermocouple of the MAX6675 is grounded, while the thermocouple of the MAX31855 is floating. And there comes additional functionality here, that it detects if the thermocouple gets a connection to ground or a connection to VCC. Another most important difference between the two you find in the absolute maximum ratings and also in the recommended operating conditions further down in the data sheets, but the absolute maximum ratings are sufficient here. So the MAX31855 runs supply voltage range minus 0.3 to 4 volts, absolute maximum. So it is a 3.3 volt device. Accordingly, all other pins, that includes the logic pins, slave out, slave clock and chip select, are specified between minus 0.3 volts to VCC, so usually 3.3 volts, plus 0.3 volts, so 3.6 volts. While the MAX6675, from minus 0.3 to 6 volts, in fact, recommended you can run it at 3.3 volts or 5 volts, at your leisure. and accordingly the digital input pins, yeah, are also compatible if you run it at 3.3 volts with 3.3 volt logic. If you run it at 5 volts, you might get away with 3.3 volt logic levels, but yeah, it will work at 5 volt logic levels for sure. Now, there's absolutely nothing in the Maxim's documentation for the 31855 to suggest that the other pins, that is your digital input pins, are 5 volt compatible or 5 volt tolerant or 5 volt whatever. Fact is, if you put 5 volt at the digital input pins in any form, you exceed the absolute maximum ratings and you run the risk of destroying that chip. I just, yeah, make such a big point out of that because, yeah, these boards with just the chip and the decoupling capacitor for VCC are sometimes advertised as 5 volt tolerant or 5 volt compatible. They are not. I even seen a video on YouTube where a guy shows the MAX31855 in conjunction with an Arduino Uno, stating that they are 5 volt tolerant. They are not. You run the risk of destroying the chip when applying 5 volt to the digital pins, while you have to run it on 3.3 volts. I'm getting good at that datasheet origami. Anyway, the 31855 is more than 2 times faster than the 6675. It needs only a maximum of 100 milliseconds for temperature conversion, while the 6675 needs a maximum of 220 milliseconds per temperature conversion. Last but not least, maybe even more important than the 3.3 versus 5 volt stuff. At almost the end of the datasheets within the applications information, you find in the chapter of noise consideration that both chips require an 0.1 microfarad bypass capacitor on the power supply, which chip doesn't. And that's it for the MAX6675. However, for the MAX31855, it is strongly recommended to put a differential capacitor of 10 nanofarad between the thermocouple input pins. In regards to that 10 nanofarad differential filter capacitor at the thermocouple inputs of the MAX31855, strongly recommended is an understatement. I wasn't able to get that Chinese breakout board working without modifying it by adding that 10 nanofarad differential filter capacitor at the thermocouple inputs. I also got my hands on a MAX31855 engineering sample directly from Maxim and put it on my own breakout board, but yeah, the same. Without the 10 nanofarad filter capacitor at the thermocouple inputs, it doesn't work. I made a whole video about that. Yeah, a card link. So I took it upon myself to amend the typical application circuit for Maxim. Yeah, the 10 nanofarad differential filter capacitor at T plus, T minus thermocouple inputs. Footnote 1, strongly recommended. Footnote 2, in fact required. Here's the 10 nano capacitor I botched onto the Chinese breakout board. Yeah, I just used the pins from the terminal block. And here's the 10 nanofarad capacitor on my own breakout board with a Maxim engineering sample where I soldered the capacitor directly to the pins of the chip. Much better solution, but this seems to work too. So the question is, how do we interface our 5 volt Arduino, here my trusty Nano, with this 3.3 volt chip? And the answer is actually easy, kind of. So here's my Nano and the MAX31855K module as they reside on the breadboard with the pins roughly in the correct physical location, and I haven't drawn all nano pins, just the ones that I need at both ends of the nano board. First, the power supply. That's an easy one, cause the Nano has a 3.3 volt regulated output here, so we just have to route that to the VCC pin of our MAX module. Second, the slave out pin of the module to the master in slave out pin D12 of the Nano. Here it gets a bit dirty. The output levels of the MAX31855 at 3.3 volt power supply are for high a minimum of 2.9 volts and for a low signal a maximum of 0.4 volts. While the input levels of a Nano, an 80 mega, at 5 volt supply voltage is a high a minimum of 3 volts and a low can be a maximum of 1.5 volts. So at the high levels we are 100 millivolts off, but that will work. Third and fourth, the chip select line D10 from the Nano to the chip select pin of the module and the slave clock D13 pin of the Nano to the slave clock input of the module. Of course, the MAX expects 3.3 volt logic level signals, while the Nano is putting out 5 volt logic level signals. And there are many ways to skin that particular cat. I choose simple voltage dividers here with 2 resistors each to translate the 5 volts down to 3.3 volts. And we don't have to talk about number 5, the ground connection. That's self-explanatory. And that's how it looks on the breadboard. So we have our master in slave out D12 going to our slave out pin here at the module. We have D13, our slave clock, here with the voltage divider going to our slave clock on the module. We have our chip select here going through a voltage divider to the chip select. We have our ground connection and we have our 3.3 volt power. That's it. Now let's whip up some software and read some temperatures. And here's the code. And I didn't really have to whip up something. That's basically an example from Rob Tillaart's MAX31855 library, and it works like a charm. I modified it slightly. We'll have a look at the code in a second. But anyway, you see here you get a raw data that's 32 bits from the MAX31855. That raw data includes a lot of status information, almost 8 bits, 5 bits at least. It returns you the internal temperature of the chip and the thermocouple temperature. Isn't that great? And it's really working, because if I heat up the thermocouple, then you will see, mouse with the left hand, you see the thermocouple temperature rising. Yeah. And guess what happens if I touch the chip? Danger mouse and double trouble. Who can remember that? Oh, look. The chip temperature is rising. Who had thought that? Anyway, onwards to the code. It's really simple. As I've mentioned, I'm using an example that comes with Rob Tillaart's MAX31855 library, and that library is available within the Arduino Library Manager. There are 2 or 3 other libraries available there for the MAX31855. I had a closer look at the Adafruit one, but I didn't like it too much because it has additional dependencies. You need to load more Adafruit libraries to get that going, and it has some other drawbacks. Anyway, Rob Tillaart's stuff is usually very good and very lean. I did modify his example a wee bit, just some serial print stuff where I changed the formatting and the labels a little bit. Nothing too much. To use the library, you have, of course, to include it here. Rob Tillaart included in his library some pin information for the Arduino Uno and an ESP32, as well as some timing information for the read method of his library. We will see that in action further down below. You have, of course, to define a chip select pin. That's 10 in our case. We saw that in schematic. And you have to create a MAX31855 object passing the chip select pin. That's for hardware SPI. The library also supports software SPI. There you have to pass an addition, a slave clock pin and a master in slave out pin. Moving on to the setup, not much happening there. We do a serial begin because we want to print out information to the Arduino serial monitor. And we use the begin method for the max object to get it going. The code in the loop is also quite simple. First, we have to call the read method, which is actually reading 32 bits from the max via the SPI bus. We saw the timing for the method above. And please note, everything else does not do any work on the SPI bus. It just extracts data from these raw 32 bits. The method also returns a bit array, 8 bits, with the error bits from the max, for example, thermocouple short to ground, thermocouple short to VCC, and so on. And I print that out here. The getRawData method returns you the last 32 bits that you have read. Printed that out too. And the getInternalTemperature method gives you the internal chip temperature extracted from those 32 bits. And finally, getTemperature gives you the actual thermocouple temperature, also extracted from these 32 bits. And then we have to do a delay. At least 100 milliseconds, minus how long that stuff takes according to the datasheet. Remember that. Here we have a slow 1000 milliseconds. And that's all. Are you ready for a bit of bit banging? First, you've probably noticed that I'm now putting out the thermocouple temperature, blue line, and the internal chip temperature, red line, onto the Arduino serial monitor. Second, I want to point out that the thermocouple temperature has a good 3 least significant bits noise on it. We saw the same thing with the MAX6675 and we solved it there by using a moving average filter. I already caught the video, link in the description. I won't repeat that here, just look at the older video. We are at number 4. I'm no longer using Rob Tillaart's excellent library, but now do all the bit banging myself, just relying on the standard Arduino SPI library. Fifth, my code is really working. So we can heat up the thermocouple and everything is fine. I'm not just measuring noise here. Okay. And number 6, meanwhile I shaved. Okay, get over it. The code. As I've mentioned, I'm just using the standard Arduino SPI library. And first I define the number of maxes I have on my SPI bus. The code is capable of handling more than one chip on the bus. Accordingly, I store my chip select pins, it's still the digital 10, in an array, not single variables. Then we have some constants. We will come back to those later. I also need some SPI settings for my MAX31855. It's 60 MHz, basically the maximum SPI clock, MSB first and SPI mode 0. In the setup, I go through all my chip select pins and define them as output and set them high, so disabling the chips. I also do a SPI begin to prep the SPI bus, and I do a serial begin with 1 megabaud, the fastest that's possible, because I want to print out something to the Arduino serial plotter. In the loop, I define 4 variables: the thermocouple temperature, the internal temperature, fault bits, which is just a byte, so a bit array, and a variable I need later for a loop. I do a delay of 100 milliseconds. Remember the data sheet, the max needs at most 100 milliseconds for temperature conversion. Then I do a loop over all my max chips that I've defined above. And I call my MAX31855 read function, which gets the chip select pin as arguments and pointers to the other variables. And the function will write, hopefully correct, or it does correct values to all these variables. Then I do a serial print of the thermocouple temperature and internal temperature. And finally, I do a print ln if I'm finished with all my max chips. Before we dive into the bit banging, a quick look into the MAX31855 datasheet. You get 31 bits of data from the max, and I will read them into 2 unsigned int 16-bit variables, data0 and data1. Remember, most significant bits first, so the higher bits 31 to 16 land in data0 and 15 to 0 in data1. The bit banging happens within my MAX31855 read function. We already saw the arguments. Please remember, for the temperatures and the fault bits, I'm just passing the pointers. And here we have the 2 unsigned int 16-bit variables, data0, data1, where I will store the data received from the max. And to receive the data, I first set the chip select pin, passed above, too low. Then I do a SPI begin transaction with the SPI parameters we created in the very beginning. And then I get with SPI transfer 16 the first most significant 16 bits and store them in data0. And then I get the lower 16 bits and store them in data1. I do an SPI end transaction because that's all we do on the SPI bus. And I set the max chip select pin again to high. Next, I want to extract the fault bits, which I marked yellow. The first one is the least significant bit in data0, and then we have 3 more here, also the least significant bits in data1. So I mask within my data1 the last 3 least significant bits, and in my data0 with binary AND, only the very last least significant bit. I also shift that 3 bits to the left, so it ends up in this position, which is still free. I binary OR both, and that's my fault bits. Short remark in between. That's not the fastest way to do it, but it's the easiest to explain. Now for the internal temperature of the chip, which is stored in data1 in the bits 15 to 4. 15 is just a sign and 14 to 4 is an unsigned integer number. I mask the bits of that unsigned integer in data1 shift them 4 bits to the right, so they are at the very end of the 16-bit word and make sense as a number. And that number I multiply by 0.0625, which is the degrees Celsius value of the least significant bit. If then the sign bit is set, I subtract 128 from my internal temperature. And I will explain that in the datasheet. That's the data format from the datasheet for the internal chip temperature. It's 12 bits and the first bit is the sign bit and the 11 following bits are the unsigned integer we worked with. Its maximum decimal value is 2047. For positive numbers, everything works as expected. It's just binary counting, starting at 0, then 1, then 1, 0, then 1, 1, and so on. But for negative numbers, we start at the maximum possible value and then count down. So the next value below 0.0625 would be coded 111111110. The least significant bit corresponds to a temperature of 0.0625 degrees Celsius. You can derive that from this table, but you also find it somewhere else in the datasheet. And that corresponds to a decimal value here of 1. The decimal value of 2047 corresponds to 127.9375 degrees Celsius, their maximum number. And if you add both up, you get our 128 degrees Celsius. Now our code would handle that minus 0.625 as a positive value of 127.9375 Celsius. Minus the 128, we come to the actual value of 0.0625 degrees Celsius. And as the negative value increases, its actual positive value decreases. And yeah, we get the right negative number from that calculation. The same principle applies for the thermocouple temperature, only we have here 14 bits, 1 sign bit and 13 data bits, and the least significant bit is 0.25 degrees Celsius. So our maximum decimal value in 13 data bits, 8191, corresponds to 2047.75 degrees Celsius. So we come to our factor here of 2048 degrees C. Talking about the thermocouple temperature data, it's the first 14 bits in data 0. So accordingly, extracting the thermocouple temperature works exactly like the internal temperature. We just have to mask here 13 bits and we only have to shift them 2 to the right and we have to multiply it by 0.25 degrees Celsius, value of the least significant bit. And if the sign bit is set, we have to subtract 2048. Finally, if any of the fault bits are set, so fault bits is not 0, I set the thermocouple temperature to not a number. Coming around full circle, we are back at the byte constants I skipped, and these are just provided for your convenience, so you can analyze that fault bit bytes that is returned by the function. So bit 1 means open circuit, bit 2 short circuit to ground, bit 3 short circuit to VCC, and bit 4 any of the above error bits set. Now that was quite a ride, but then it is bit banging after all. As I've mentioned, my code can handle multiple MAX31855s on the same SPI bus, and as it happens, I have a second module here. I made that one myself, details about it in the video where I fixed the Chinese modules. It already has been carded, but yeah, anyway, link below in the description. So, how do we connect the second module? I've drawn it in here, and please note the pin out is a little bit different from that of the Chinese module. And we don't have to talk about VCC and ground again. Slave clock is simply an extension of our existing slave clock line. It's called a SPI bus for a reason, and we already translated that down from 5 volts to 3.3 volt logic level. Slave out, same principle, we just extend our master in slave out line here, and we're still relying on the fact that our 5 volt nano will somehow recognize the 3.3 volt logic signals from the MAXes. That leaves us with a chip select, and there we need of course an additional pin on our Arduino. I've chosen D9. And an additional voltage divider to translate the 5 volt logic level down to 3.3 volts. Of course, as long as you don't run out of chip select pins, you can extend the bus further and connect even more MAX modules. Here's my ugly duckling on the breadboard. That's the additional voltage divider for the D9 slave select, and it jumps over here via the green line to my module. Everything else, the bus, VCC and ground, is just extended to it. And here we see both chips in action. Yeah, green and yellowish orange is the data from my second chip. And yeah, it's working. Fire in the hole, chip number 1. Woo! Fire in the hole, chip number 2. Yep. The code change is of course trivial. I just increased my number of MAXes to 2 and added my new chip select pin to the array of chip select pins. Before we come to the wrap up, I want to make 2 more points. The first one is about mixing 3.3 volt slaves that don't have 5 volt tolerant logic pins, yeah, like our MAX31855, with 5 volt slaves on the same SPI bus. Bottom line, it doesn't work with that simple approach here. Of course, you could connect the VCC of the 5 volt slaves to the 5 volt rail and their slave clock directly skipping that voltage divider to the slave clock pin. And for their chip select pins, you also don't need a voltage divider. However, they would share the master in slave out line with all the 3.3 volt devices, and the 5 volt slaves would put 5 volt logic level on that line, and that might destroy your slave out pins of your 3.3 volt devices. So yeah, that's a no-go. My second point concerns these more complex MAX31855K breakout boards. To the best of my knowledge, the original design was done by Adafruit, but by now you get Chinese clones of them as well. Adafruit, and of course the Chinese, market these boards as 3.3 to 5 volt power supply and logic level compliant. And we're talking here not about any imagined MAX31855K 5 volt tolerance. That doesn't exist. Yeah, remember the stuff with the datasheet in the beginning. But about actual circuitry on these breakout boards that make them 5 volt compliant. However, if we have a look at the circuit diagram of that Adafruit breakout board, we see that the data out pin, and I called it in my schematics a slave out, of the MAX31855 is directly connected to the jumper. That is, if you have 5 volt devices present on your SPI bus, you get a 5 volt level in here and you fry your chip. Logic level shifting for the chip select and the slave clock is of course done here, just with a little bit different technique than we used. As a bonus, you get a 3.3 volt regulator on these breakout boards, so you can feed 5 volt into the VCC. However, if you are working with Arduinos, they already supply you with a 3.3 volt rail. Yeah, we used it. The input filtering on the thermocouple pins on these breakout boards is very good. Not only do you get the strongly recommended 10 nanofarad capacitor here, but also 2 ferrite beads. I'm sorry, but I have actually a third point to make. Like with the MAX6675, you can short out things with 2 thermocouples. Details about that in the 6675 video, it was already carded, link in the description. The 665's thermocouples are grounded, so if you have 2 of them, of course you can short things out. At a first glance, the floating thermocouples of 2 31855s have a pretty good isolation. But keep in mind that isolation comes from some circuitry in the chip that dies if you apply more than 3.6 volts. So in effect, with the 6675 you can short out things, and so you can with the 31855. The only difference is your chips work as a fuse in that case and get destroyed too. I do have a video about how to overcome that problem, galvanic isolation of SPI devices, card link. So, what's the verdict? Adafruit markets its MAX31855K breakout board as an upgrade to the MAX6675. I'm not so sure about that. The MAX31855K has a wider temperature range, yes, but it doesn't have a higher accuracy or a higher resolution. Like the MAX6675, it has a few lSB's noise on the temperature measurements. The other differences? Well, it comes down to your design and your application, if you count them as pros or as cons. Okay, the 31855 also gives you the internal chip temperature. But the other things, well, if you have a 3.3 volt MCU, you will probably go with the MAX31855K. If you have a 5 volt MCU, yeah, like my Arduino, you probably won't go through the trouble using the 31855K unless you really need its extended temperature range. The 6675 has a grounded thermocouple, so you can at least connect it without isolating it to, for example, a heatsink that is also referenced to ground. The 31855 has a floating thermocouple, so you cannot reference it to anything. You always have to isolate it. So, in my book, these chips are simply designed for different applications, and the 31855 is not intended as a direct upgrade of the 6675. That's it for today. I'll put a link to the code I used here in the description. Until next time, bye!